Hello everyone, so this is part 2 of our solution of the problem that was given last time, the resistor, inductor, capacitor series circuit with voltage given by V0 sine of omega t. We have mentioned in our previous video that to solve the general solution, we have to look for the homogeneous solution and the particular solution. And in the first part, we were able to calculate already the homogeneous solution, which means that we are only left with calculating the particular solution for this problem. Just to recall, this is our homogeneous solution last time. And our only problem right now is to look for the particular solution and add it to the homogeneous solution so that we can have the complete solution for our second order ordinary differential equation for the RLC circuit. So just like last time, we also provide a step-by-step solution for this, or derivation, as the case may be, so that we will not be lost. And it's actually easy to understand certain physics concepts or physics problems when we have a step-by-step structurized solution. So the first one is to consider an ansatz. But before that, we recall that what's our problem before? Our general equation. We have here our general equation for the RLC circuits by applying the Kirchhoff's voltage law and then differentiating with respect to t. So we first copy that here. We recall that this is our equation. So here in the homogeneous solution, we take note that we equate this to 0 since it's homogeneous. So the answer, of course, should be equal to 0. But here for the right hand side, in looking for the particular solution in the right hand side of the equal, that is, we have this one, right? So we try in finding the particular solution, we try IP. This is actually an ansatz, right? So we cannot be wrong with this choice because we will be testing this, and at the end of the day, at the end of the solution, we can see that indeed our solution is correct for this. So we propose this ansatz, this general solution for the particular solution. We have b plus b, we have plus b sine of omega t, and of course the caveat is that there must be the same frequency undetermined. Of course, we have undetermined coefficients, so you just have to remember this ansatz. Let me just, and then we restart numbering. This is number 1. Okay, so our general equation would now be like this. So we first get the derivatives. This is our ansatz for IP, which means that our IP dot is equal to, so we derive this, so that's negative a cosine, derivative of cosine is sine omega t. Yes, so that's sine omega t plus times the derivative of, omega t, so that's omega t, that's omega. Yes, that's right. Plus, we have b cosine, b omega, cosine of omega t. Okay, so that's for the second derivative. For the first derivative, wait, let me just change this to have a proper notation. So that's AP. And we have the second derivative. We have IP double dot. We have IP double dot is equal to So what's the derivative of this? So that's negative a omega squared. Omega squared. Why is this? Why is there a dot here? Wait, let me just make sure that this is correct. IP. And this is negative a omega sine of omega t. Okay, so for the second derivative, this is, let me just transfer this to the second line. Wait, okay, it's okay. So we have negative a omega squared, derivative of sine is cosine, so that's cosine of omega t minus b omega squared sine of omega t. Or simply, this means that our IP I think this is okay. We have omega squared. Okay, so this is okay. So we just substitute this. Our answers. Substitute. We have IP. We have IP dot. IP. Of course, these are all functions of t, right? So we have and IP double dots. IP double dots. We have IP double dots. Okay, so substitute this to our ordinary differential equation, to the ordinary differential equation, which is this one. Okay, to the ODE to, okay, this one. 2, so substitute this 2. Now what will happen to our equation? This will become L times I double dot. What is I double dots? This one. So we have negative a omega squared cosine of theta, cosine of omega t minus b omega squared sine of omega t. So we just place it here. Yes, that's correct. And then R, the first derivative, so we copy this. We have R times that quantity and then plus 1 over c times I. So what is our I? This is our ansatz. So we copy this and then substitute it to our equation. Of course, this is equal to omega times v naught cosine of omega t. Okay, I think I have to change the layout for this so that it becomes clear. Let me just change the margins. We have 0.25, 0.25, 0.25, and 0.25. So that we can just increase the font size of our equations. Okay, so we now have this equation upon substitution of our IPs, right? Anyway, this is IP. I think that is quite understandable in this case, just like what we did with the homogeneous solution where we substituted I's with IH. But in this case, since we are calculating the particular solution, so that's IPs. Okay. Now we can notice that we can actually group this into two. We can group those that contain cosine and those that contain sine. But before that, it's better if we can expand this so that we have negative L A omega squared cosine of omega t plus minus. So we have minus LB yes, sine of omega t. It becomes simpler actually if we distribute this to the parentheses. Minus RA sine of omega t minus RA omega sine of omega t. We have plus RB, and then we have omega cosine of omega t plus we have A cosine of omega t. Okay, this is A, this contains A. So we have plus this is A cosine of omega t over C, or simply I think it's better if we put A over C and then cosine. I think that's simpler to look. Plus we have B over C and then sine of omega t. Sine of omega t. Okay, and then this is equal to, of course, omega times V naught cosine of omega t. Now we can group this, as I've said, into cosines and sines. So it's better if we put into box those that contain cosine. We have this one, and then what else? Sine, cosine. We have this one. I think I will just copy this for uniformity. So we put it here containing cosine. What else? We have the A over C as well, contains cosine, right? So we have this one. And then for the sines, maybe we can put them inside a circle. This one. So we have here the sine. Let me just change the color into green. Wait, okay. And then just copy this one. We have this also contains sine function. What else? We have B over C sine. It's also worthy to note that the right hand side of the equal contains cosine, and it's very important because we will be equating this to the right hand side, particularly to those that contain the cosine function. So we can group this. We have cosine omega t, this one, let me just change this, times LA squared negative LA omega squared. I'm just copying. LA omega squared plus R omega times B cosine plus A over C. Yes, plus A over C, and then we equate this with the right hand side. So this is equal to omega V naught. Here's the omega. Let me copy the omega here. So we have omega V naught cosine of omega t. And for the sines, I think I will just make this another step out of the way. Another step, we have group terms, grouping of similar terms. So for cosine, we have this one, and for the sine, we have sine of omega t times negative L times B times omega squared minus R omega. Let me just copy the omega. R omega times A. What else? Plus B over C. And we can notice that there is no sign on the right hand side of the equal, so this is just equal to 0. Now, of course, we can cancel out cosine in the first equation here, the equation above. So we have cosine, we cancel this out, and the same as well for the right hand side, so that what's left for this equation is only this one. We have equals omega equals omega v naught. So we have these two equations, one for those that contain cosine, and the other one though for those that contain sine, which means that this could also be written like this. Okay, so this is now our guide equations. These are our guide equations. So we now have a system of equations, two equations. I will just call this as step 6, so that we can have this equation. Let me just group this one. How do I group this? Wait, let me just find it here. Yes, particularly this. So we have this equation right here, and I think there's a problem with this. Okay, anyway, let me just write it down again. So that's A times negative L omega squared. Let me just copy omega. Okay, omega squared plus 1 over C plus B times R omega. And this is equal to omega v naught. And then for the second equation, we have A times a negative R omega plus B, right? We have minus L omega squared plus 1 over C. Okay, I think, yes, this is correct. And this is equal to 0. So we have two equations and some unknown coefficients. Now, to solve this, it's better if we get the ratio, or we solve for the ratio. Solve for the ratio. And that is from the second equation. From the second equation, we can immediately see that A is actually equal to, so what's the relationship? That's A is equal to B dot, or B times, we have this term, we have negative L omega squared plus 1 over C over, we have R, yes, RW, R omega, over R omega. And we can actually write this as negative B over, or B times S over R, where of course we have our S is simply equal to omega L minus, what is this? We have minus 1 over omega C. So 1 over omega C. And this is our, if you can remember, this is the equation for our reactance. Okay, so anyway, so we now have here A, and through this we can also find the value or the equation for B. So we have substitute A into the first equation. We have, what happens now is that we have negative B times S over R times negative L omega squared, right? Plus 1 over C times, is it times? Yes, it's plus B times R omega. And this is equal to omega V naught. Okay, but we have to take note that we have negative L omega squared plus 1 over C equals, this is minus, let me just move this, minus omega L minus 1 over, we have omega C times omega. Yeah, so that's times omega, or we can write this as minus S omega. So that we have B times S over R times, I think I will just use that. We have times S omega plus B times R times omega equals omega V naught. And this actually implies that our B omega times, what is this? S squared over R plus R equals omega V naught. Anyway, we are just playing with the equation right here. So this is quite very straightforward. We are just doing substitution method, which means that B equals V naught R over. So that's V naught R over R squared plus S squared. Perfect. So that's our B. Let me just put them into a box. We have, this is our A. So that, again, so that it's easy to actually go back to them once we need them. So we have no field. That's okay. And then this as well. We have this one for the value of our B. Okay. Then from here we have A is equal to negative, we have V naught times S over R squared plus S squared. Okay, so we are now done with calculating our coefficients A and B. Let me just put a box here so that it's easy to find this. So this is step 8 of our calculation. Anyway, if you have questions, you may just please write down your questions in the comment box, and I will answer your queries or questions. So the next step is actually to find for the amplitude phase form. Now that is, we find for the magnitude I naught. And this is mathematically, this is actually just the square root of A squared plus B squared. And of course, this is equal to V naught let me just put a fraction. So we have V naught over R squared plus S squared. So that's over R squared plus S squared. And this is our, we can define our impedance here. Impedance, Z is equal to R squared plus S squared actually. So you have R squared plus S squared. So that's, this one is actually V naught over our impedance. And the phase is given by tangent of phi. Let me just, tangent of phi is equal to negative A over P, or this is equal to simply S over R. Thus, we now have our solution, or our particular solution, as a function of t. This is equal to I sub O sine of omega t minus phi. Where is our omega? Let me just look for omega. So we have sine of omega t minus phi, and this is equal to a V naught, or V sub O. V naught over the square root of R squared plus R squared plus S squared, or simply just the impedance, times sine of omega t minus phi. So that's omega t minus phi. So this is now our particular solution for this problem. And having calculated already our particular solution for this, it is just worthy to combine them with the homogeneous solution, the complete solution for the RLC circuit is, we have I as a function of t equals, we just have to combine the homogeneous solution and the particular solution. So this is our homogeneous solution. We just have to copy. We have, this is IH. IH as a function of t plus IP as a function of t, or simply we have IT, I as a function of t equals, right, this one, okay, plus I think this is straightforward. We just have to put it down right here. So you have plus V naught over the impedance R squared plus S squared times sine of omega t minus phi. And this is now our general solution for the RLC series circuit. So with V as a function of t with our voltage given by V naught sine of omega t. And we can interpret this, or the physical interpretation of this is that steady state current oscillate at a driving frequency omega. So we have here our driving frequency omega, but lags by our phase angle phi depending on the reactance S. That is, the inductive S greater than 0, or as S is positive, it leads to voltage. And if capacitive, that is negative, it lags, right? So that's it. This is the complete solution for our RLC series circuits. I hope you've learned something, and if you have questions about the derivation of this, you are free to ask questions by typing your questions in the comment box. Thank you very much, and that's it.